There are a few special points to be able to identify when you have an energy diagram. One is where you have maximum potential, and that's going to be wherever you have your potential energy line, the one in blue, intersecting with your total energy line, which is the horizontal one, which is kind of a brownish color here. So that's where you have maximum potential energy, because at that point, kinetic energy is equal to 0. So these two things are actually the same point. So wherever your kinetic energy is 0, that's where you have maximal potential energy. That's where all of your energy is potential. Now, on the other hand, your point of maximum speed is going to be at the minimal potential. Now, the reason that I'm not necessarily saying 0 potential is, for instance, you might have a ball that can't actually fall all the way to the ground for whatever reason. So the max kinetic corresponds to the minimum potential. So those are going to be your lowest points. Now, there's going to be other things that we talk about, including equilibrium and turning points, but let's just start and talk through what's going on here. Now, this energy diagram is not for gravity, and it's not for a spring. It's some sort of general energy diagram. And again, you might think about this as a roller coaster where this is the x position, so the distance along the track, and because the track has different heights, you have different potential energies where that's actually gravitational. So it's not free fall potential energy, but say on a roller coaster. So if we let our object go at this point, it's going to, and we'll talk about this in a little bit later, but basically roll downhill. And so it is speeding up as it travels this way. How do we know that it's speeding up? Well, at that initial point, kinetic energy was 0. When it gets to this point, this is how much kinetic energy it has there. Remember that the difference between these two gives you Ke. It's then slowing down through here, which we know because we see that the distance between these two are getting smaller. It crosses over this bump, and it speeds up again. It's going faster here at x4 than it was at x2 because the distance between these is greater. When it gets back up to x5, note that there's again an intersection point between your total energy and your potential energy. So at that point, Ke, kinetic energy, has to equal 0. So if kinetic energy equals 0 at that point, then it must have stopped. Now, it's not just going to stay there, it's going to turn around and come back. So you don't necessarily know what direction it's going unless you're explicitly told where it starts, but otherwise you should be able to infer where it has higher speeds versus lower speeds. And these turning points are any place that your total energy line intersects with your potential energy line. That corresponds to kinetic energy of 0, and that's going to be where your object actually stops and turns around. Now remember that the total energy line depends on your particle, so for the same roller coaster track, we could actually choose to start our particle in, for instance, a different place from rest. If I started it here from rest, we would have a new total energy line. We can't use that line. So this new total energy line intersects the potential energy curve at the point it's starting from, since it's starting from rest. And we then see it's again going to speed up, but now it has a new turning point here. So what that means is at that point, kinetic energy is 0, and we're going to see that an object we start here is actually just going to go back and forth in this little dip. It never makes it over that curve because it doesn't have enough energy. So turning points can only be evaluated based on the total energy line of your object. Equilibrium positions are positions where the derivative of the potential energy curve is 0. And you can have stable equilibrium or unstable equilibrium. And an unstable equilibrium, it's concave down. Stable equilibriums are concave up. What you can think about here is that if your total energy is equal to that specific energy, and we placed our object there, that's like balancing a pencil on its tip. You don't expect it to stay, but you can't exactly predict which way it's going to go, whether it's going to go to the left or the right, but we really don't think it's going to stay there. On the other hand, if we started with the total energy that corresponds to this point, and we placed our object there, it's stable. It's going to sit there very happily like a ball in the bottom of a bowl. So equilibrium positions can happen, and again, this will be helpful for more advanced physics analysis. So this is really important to be able to interpret an energy diagram. You are free to draw it as a visualization, but there are going to be many situations where that's challenging to do. So this is more something that you interpret rather than something that you draw yourself. So make sure that you remember that your potential energy curve, which the book is using here as PE rather than calling it U, but potential energy curve is going to be the distance from the x-axis, where energy equals 0, to that. That's the particle's potential energy. You then have a total energy line, and so total energy minus potential energy gives you kinetic energy. So we're only defining these for isolated systems that don't have changes in thermal energy, so K plus U does not change. Turning points are wherever your total energy line crosses your potential energy curve, because those are places where your kinetic energy is 0. It stops and turns around. The particle can never be at a point where the potential energy curve is above the total energy line. There's no way to have negative energy. So if potential energy plus kinetic energy must equal total energy, there's no way for total energy to be less than potential energy and the particle actually be allowed to get there. I defined the potential energy curve as being a property of the situation. So that's here at the system. So the spring, the mass, the spring constant, the orientation, you don't just pick whatever potential energy curve you want, but the initial conditions are what determine the total energy. So you can have the same system that you start in a different manner. Your potential energy curve would be the same, your total energy would change. Minima or maxima in potential energy curves are equilibrium, maxima are unstable, minimum are stable.